Welcome. This video is based on Andrej Karpathy's tutorial, which is fantastic in its original form. But instead of moving quickly through the code, I'm taking a slower, deeper approach. We'll go line by line, breaking things down, and really understanding what's happening under the hood. Same project, just explained in my style. So let's get on to it. I have a small text file called names.txt, which I'm going to import right here. So I am going to name that words. So open. I have a text file loaded in this directory. So you can see that in this directory I have names.txt. So names.txt, and I will like to open that, and then let's split lines. So when I do split lines, because the names are okay, you can see that in every line there are new names. So what I want to do is that I want to split by lines, and when I do this, this will be a list of words. So words is going to be list. So let us print the length of my words, which will show the how many names I have in names.txt. And then let's also see first, let's say first 8 words. So when I run this, so looks like I got an error because the text file name is names.txt. Open, and this is read more. Okay, so you can see there are 32,033 words, and then these are the first 8 names in my names.txt. Now what I want to do is that I want to create first of all a bigram model. So first of all, I'm going to suppose I have a name Emma. So what I'm going to do is, so in order to indicate the starting and ending of a word, I'm going to place a special token at end of the word. So this dot is going to be my special token that denotes starting and ending. So if dot e, then that will mean that name starts with e, and if a dot, then that means that the name ends with a. So what I'm going to do is that to make a bigram, what I will do is, so there will be Emma, and after I will skip this first token, and then I will have something like this. So I'm just explaining how I will approach creating the bigram. So later on you will understand exactly. So I have this, and now what I will do is I will create dot e. So you can see dot and then e, and then I will create another bigram called em, and then I will create mm, and then that will be a dot. So when you a dot, when you do this, so it will be ma and then a dot like this. Okay, so we have, you can see we have two character pairs for this word Emma. I have 5 different examples of bigrams. So what this means is that when I have dot as an input, I should get e as an output. When I give e as an input, I should get m as an output, and so on. So this, all this left side is going to be my input, and this right side is going to be my output. That is what I want from my neural network. So let us create bigram. So what I will do is I'll create a loop. So for let's say for each word in words, and for example, let me take just the first word. So this will be up to 1, so which means I only get Emma. So now what I want to do is I want to create a list. So I want to have dot, which is the special token at the beginning of each name, and then I will convert the word into list, and then another special token dot that indicates that the name has ended. Now I want to create another loop for character 1, character 2 in zip, and chs 1 dot. So this will exactly do something like this. So zip, what zip will do is that if there is a word dot emma dot, so chs is this, and then what I'm doing is that after 1 I'm taking all, so emma dot. And now what zip does is that it will take a dot and e, and then it will create a tuple. It will get e and m, and then it will create tuple. So exactly what I showed previously. So now here what we're going to do is that let's go inside this loop, and so basically let's print this. So ch1 and ch2. So you can see dot e, em, mm, ma, and a dot. So these are my bigrams. But you know, in neural networks we can't send characters, we can't send text, we have to send numbers. So what I'm going to do is that I'll create a new cell above this, and I'll create a chars. So in chars I want a list of a to z. So what I will do is, so to do that I can join my words. So join words, And when I join words, I have a long list of all the names concatenated, and then I want to pass this in set. So when I pass this in set, this will it will remove duplicates, so I will only get A to Z, but it's not sorted. So to sort this, I will pass this in sorted. So now I have A to Z sorted. So you can see if I print chars, I have A to Z sorted list. Now what I want to do is I want to create string to index mapping. So for each index and string in enumerate chars, so this will give me 0 and A, 1 and B. So I want to exactly map string to its index. But what I want to do is that I want to increment every index by 1, because I have a special token dot which I want to place at the 0th index. So dot goes in 0. And similarly, I want to do exactly reverse of this. So integer to string, and for each string and index in s to I dot items. So in the s to I dictionary, I want key value pairs, which is the string and the index, and I want to reverse this. So when I do this, if I print I to S, it will give me all the index and string mapping. So 1 is A, 2 is B, and so on, and finally 0th index is dot. So now I can use this here. So what I can do is I can create a bigram. I can say bigram, and I can simply uh, string to index, and I can basically pass the ch1, which will be my input. And okay, let's do one thing. For now, I'm just going to show you words, but later on we'll use this because I want you to visualize this. So I will create a dictionary called B, and this B dictionary will store all the counts of my bigrams. So how many times dot E is present in my words? How many times is EM present in my words? So I will count that. So what I will do is I will create a bigram, and I will create a tuple ch1 and ch2, and in B, by bigram, I want to get in B, I want to get that bigram, and if there is no bigram, I want to get 0 and then increment by 1. So every time I see dot E, if in the first time, if there is no bigram, then it will create a key of this bigram, and it will value will be 1. And each time it sees dot E, it will add 1 and 1, and in this way we can store counts of each bigram. So if I run this, and if I print B, then you should see dot E is 1, EM is 1. So every bigram is 1 currently. But if you see in the first 8 words that we printed here, A, there are several words that end with A. So if I take first 4 words, then okay, let me take first 4 words, then what I should get is A dot should be 4 times. So you can see A dot is 4 times because A dot bigram occurs 4 times. A is ending 4 times. Now instead of doing this, what I want to do is I just don't want to take 4 words. I want to take entire words, and let's run this cell and let's visualize B. So you can see I have counts of every bigrams. Now let's see which bigram occurs the most. So I want to sort my B dictionary. So in sorted, I want to pass B dot items, but by default it will sort using this key value key pair. So I want my key to be lambda function. Key value will be my input, and in key value I want not the 0th index but the first index. So I want to sort by numbers. So first, and let's do negative so that I get in descending order. So the most repeated bigrams comes in the first. So you can see n dot is the most repeated bigram, which means that most of the words start with M, most of the words end with A. An bigram repeats 5038 times. So this we have successfully stored all the bigram frequencies. But I want to visualize this more. So what I want to do is I just don't want to store in a dictionary. I want to store this in an array, two-dimensional array. So what I'll do is I'll create a two-dimensional array. So first of all, before doing this, to create a two-dimensional array, I will import torch, and n will be my two-dimensional array, torch dot random n. So rand n will create a Gaussian distribution, and inside rand n I can pass the shape. So I want 27 by 27. So 27 characters followed by 27 characters. So there are 27 possibilities, possibility of character following 27 possibility after the first character. So it will be 27 by 27, and mm, this is my array. So instead of rand, what I can do is I can do zeros, because first of all I don't want any counts. So when I do this in n, if I visualize n, you should see 27 by 27 uh, two-dimensional array. But counts is always integers, so I don't want floating. So what I can do is here I can data type, I can do torch dot integer 32, and when I do this you should see every integer. And if I do dot shape, you should see 27 by 27. Now in this two-dimensional array I want to fill out these numbers. So what I'll do is I'll copy this code. Let me paste it here. For each word in words, we have dot list, we have enumerated this. Now what we will do is, now to store something in two-dimensional array, now we need numbers. So what we did here, now this will be used right here. So we have character 1, character 2. So string to integer mapping. So if I pass ch1, it will give me the integer of ch1, and I will name this ix1. And similarly ix2 will be string to index of ch2. Now in my n, I will go to ix1, ix2, and each time I will add 1. So this way it will do the same thing we did in dictionary B, but this time in two-dimensional array. So if I shift enter, so okay, so now if I see n, you should see all the numbers have been populated in this two-dimensional array. So now instead of visualizing like this, let's visualize using matplotlib. So what I will do is let's import matplotlib dot pyplot as plt and matplotlib inline. So plt dot figure, my figure size I want 16 by 16. So this is my figure size. So 16 width, 16 height, and then I want to plot this n. So plt dot I am show n, and I want to plot the uh, I want to plot using the intensity. So if some bigram is too much repeated, then I want to increase the intensity. So cmap equals to those. So if I run this, okay, I get an error. So the error is that you cannot single artist in more than one figure. So okay, so this is not figure, this is fig size. So sorry for the typo, fig size. And you can see that the matplotlib, but this is clearly not readable. We don't want our matplotlib to be like this. So I want some text to be in this each cell so that I can visualize. So let's loop in every row. So for I in range, so each 27 rows and each 27 columns. For j in range 27, and then my bigram text. So I, in each cell I want to show bigram text and the intensity, which is the number how many times the bigram has been repeated. So I to s of this I plus index to string of this j. So this will give me concatenated bigram text. Then plt dot text in ith jth ith row jth column, I want that bigram text. And horizontal axis I want to be center. So horizontally, so horizontally I want center, and vertical axis I want let's say, okay, where I want my text. So I want text in bottom, so bottm bottom, and then let's give color as gray. And similarly I want to show the number how many times the bigram has been repeated. So plt dot text I j and my uh, frequency is in this n two-dimensional array. So n j I, and horizontal axis center, and let's place this as vertical axis as top, and color to be gray. Now plt.x is off because I don't want unnecessary lines. So let's run this, and okay, we can see, okay, this looks horrific. That is because this gives me tensor. So basically what it's happening is that, so torch dot tensor 7, so this is the tensor, but if I do dot item, it will just give me the number. So right now the tensor is being printed, so if I do dot item, this will give me just a number. And okay, now the everything looks good. So these are my okay, here I have starting, and here I have ending. So a dot is dot a means how many times a has been started, so 6640. So let's do one thing. I want all my starting in this here in the first row, and then in the first column I want all the ending. So I want just opposite. So what I will do is j i j I, and then here I will do I and j. So this should probably, okay, so I have all the starting here. So you can see that a dot is 4410 times, b is 1306 times, a ends with 6640 times, and then b a repeats 556 times, a h repeats 2332 times, and there is no example where dot and dot bigram exists in our names.txt, so you can see the count is 0. So we have properly rendered everything in two-dimensional array. We have visualized using matplotlib. So AB repeats 5401 times. So here, okay, let's double check from here. So AN repeats 5438. So A and then N 5438. So our matplotlib visualization is correct. Now we have everything ready. Now we can sample out. So let's do the fun part. So let's sample out names. So sampling means that I want to generate names based on this counts. So which means that, okay, let's understand this intuitively. If BA repeats 321 times, then it means that BA should be repeating, right? If dot dot bigram does not repeat, then it means that while we sample, dot dot should not be, we should not see dot dot while we sample names. So this is kind of our main thing that we need to sample. So but first of all, what I want to do is, it would be very beneficial if we convert this to probability. So to convert this into probability, what I will do is I'll create a cell above, and then P is going to be a probability, and I will convert my n to float, and then store it in P. So when I do that, what I can do is P will be P divided by P dot sum 0, and then keep dimensions as true. So when I do this, so this will give me the sum of so when I divide P, which is the count in float, float data type, and if I sum that with so let's say if I sum every of these counts, then I'll get a number. And if I sum this every count in this row, I'll get another number. So I'll basically get, if I sum all of this, I'll get basically a column vector, which means I have one column. And now I if I suppose, if I divide this count by the sum of entire of this row, then I'll get the probability how much dot a bigram should repeat. So that is what we're trying to do. So if we run this, uh, now if we run this, we should see that if I do p0 dot sum, this should give me 1, because the probability should be 1, but it gives me 7. And I've done this in purpose because If we do 0, that means we're summing all uh, columns, which means that we're getting a row vector. So this doesn't work. If I do 1, then it will give me sum of each row, and then if we go on the first row and calculate the sum, this should give me 1. So now it works perfect. Now another thing to keep in mind is that if I remove this keep dims equals to true, and if I do the same thing, 0 dot sum, you can see uh, everything basically uh, doesn't work. That is because let me explain this. Okay, so first of all, p is what is the shape of p? The shape of p will be 27 by 27, right? And then when we sum all the rows, then we'll get a column vector. So that will be p dot sum 1 will be a column vector, will be 27 rows and 1 column. So now if we don't have keep dimensions as true, then we will not have this one will basically be removed. And then what it will do is it will basically everything will not work as expected. But if we do keep dimensions as true, so if we do keep dimensions as true, then this one will be preserved. And then in according to the broadcast rule, what will this will do is that it will do 27 by 27, which means that all the column vector will repeat, and then we'll divide this to tensors, two-dimensional tensors, and then we'll get something, we'll get everything expected. So if we do this, then we should see the sum should be 1. So this is how it works. So now we have the probability. Now let's sample out. So first of all, my index will be 0 because I want to start from dot token, because my dot is index 0. So that's why I've kept index as 0. And now I will create out, which is something that I will append all my names on. And I'll create a loop. So while true, and from my probability, I will pass the index. So if I pass index 0 to my probability, it will give me, it will basically give me um, this tensor. And from this, what I want to do is I want to pick one tensor. So basically these are probabilities. So I want to pick one probability. So if the probability of something is high, then I want to pick that. So if the probability of, let's say for example, this is high, then what we do is we've picked dot a. So a should be our starting. And then what we'll do is that if a is the starting, next time we'll go here in this row, and then from here also we will select one probability. And then let's suppose we pick g. So we have ag. Now again from g we'll pick another one probability, and then we'll keep on doing this, and then we'll have a word. And then as soon as we get any probability from this column, which is the ending. So if I get index 0, then that means that g dot means end, right? So if I get index 0, then that means my name has ended. So that is what I want to do. Now to pick uh, the probability from this tensor, what we will do is we have torch dot multinomial. You can search how it works. So you can see it returns a tensor which is sampled from a probability distribution. So exactly in this torch monomial, we'll pass probability distribution, and we'll say that we want one sample. And basically if this is a tensor, I don't want tensor, but I want the value inside the tensor. So I will do dot item, and then I will store that as a new index. And then in out, I will append that index. And if index is 0, then I want to break. And if not 0, then we'll keep on repeating. And then at the end, let's print everything in out. So I will join the out list, and in out there is index. So for each index in out, I want to map to string. So when I do this, I should give the name. So you can see the name we get is C like gra. Again, if you do this, LLY, CN, CIL. Okay, so this is some name. So let's sample out 10 names. So for in range 10, and let's place this inside this for loop, and we get 10 samples. So M, CA, Son. You can see these names are not pretty good. So if we do this again, we can see that the names are okay, but this is a good name, Trin, uh, Makis, John. So you can see that this is giving names, but okay, now it's not good. So you can see that the names, I'm getting the names, but these are not name like. And that is because everything we're doing is basically we're picking up from the probability distribution. So we took our names.txt, we split that into bigrams, and then we counted how many times the bigram occurs, and then we just converted this into probability distribution, and then we selected every time we selected bigrams, one based on one character we predicted another character, and until we hit index 0 we just kept on printing this bigrams. So that is how it is working right now, and this is not good. So these names are not good. So I think you already understood how this approach is not good, and to tackle this approach we're going to use neural network. But before using neural network, I want to introduce you one more thing, which is in every machine learning project we have to predict loss. So what loss does is that we want to predict how bad our model prediction is. Now if our model is very confident on wrong actual uh, actual thing, then the loss would be high. So predicting loss is very important because that is what we want to decrease, that is what we want to lower in machine learning. So what we'll do is we'll calculate the loss, but this is not even a neural network, but let's predict the loss. So what I'm going to do is uh, so I'm going to copy this code, this exact code, and when I copy this, okay, so I have character 1, character 2. Now instead of uh, I want to index in my P, which is my probability distribution, and I will have this, so I will get probability distribution, and I want log likelihood. So log likelihood is a number. So basically log likelihood is when you multiply all the probabilities, when you take log of all the probabilities and sum them up, you will get log likelihood, and that is what we want to maximize. So these are my probabilities. So let me store it in prop, and if I take log, so torch dot log of this probability, then I'll get let's store this in log prop, and what I can do is I can just log like log likelihood, and each time I want to add this log prop, so this will give me log likelihood. So let me print log likelihood. So this is what we want to maximize, but this will be a very big number which you will visualize. I will run this cell, then you will exactly know what I'm saying, but this will be a very big number. And what we'll do is uh, we want to find out negative log likelihood. So negative of log likelihood, so negative log likelihood, and then what we'll do is we want to average this out. So oops, so n will be 0 at the beginning, and each time in each bigram sample we'll add 1 to n, and then let's print negative log likelihood also, just so that we can visualize. And let's print the average, so negative log likelihood divided by n. So this is what we want to maximize. And if you want to maximize some, so maximizing something is same to minimizing so if okay, so okay, let me run this cell, then and you'll understand. So when I run this, you can see that the log likelihood is negative this, So if I want to maximize negative quantity, then that is same as maximizing the positive quantity. So now I want to minimize negative log likelihood. And then if I take average, then I'll get 2.45. And this is what I want to minimize. So this is my loss, which I want to minimize. So I hope you can see this. But the problem here is that I don't know how to minimize loss in this in the architecture that I've just followed. There is no way for me to decrease the loss because this is constant. The probability distribution is constant. So I don't know how to minimize this loss. So in this situation comes neural network. Now let us follow neural network architecture and then let's approach the problem. So neural network architecture. Now comes the fun part. I promise you this is going to be so fun. Now we have understood the basics. Now the fun part is coming. Now what we want to do is I will approach the problem in neural network architecture. So let me copy this text. So when I copy this, so now I don't need to count bigrams because now we're following neural network architecture. And let's take first 5 words. And then let me also print out ch1 ch2 just so that you know that what we are doing. So this is giving me bigrams dot e em mm. So these are just bigrams. Now what I told you before is that all of this on the left should be my input and my neural network should give me the output which are in the right. So if I pass dot, I want my perfect neural network model to give me e. When I pass e, I want my neural network to give m, so and so on. So left side is going to be my input and right side is going to be my output. So let us create two array, x and y. X I will put input, in y I'll put the output, but I cannot put string or text. I have to put numbers. So I already have the mapping ready. So string to index ch1, this will give me, let's say I want to append this on x. Okay, so this is going to be my input, and string to index character 2, this is going to be my output. So I will append this in y. So when I do this, I have my x and y ready. And after this, let's convert this x and y list, Python's list, to tensor. So torch dot tensor x, because we will be working on multiple dimensions. So we want to convert this to tensor right now. So torch dot tensor y. So when I do this, let's visualize how x looks and how y looks. So this is exactly the same, but we have integers. So when we have 0, we want 5. When we put 5 on our neural network model, I want 13 as output. When we pass 13, we want 13. So basically these are the index, right? So 0, 5, 5, 13. So I hope you get it. So let us see the shape of x. So the shape of x is going to be 32 and y is the same 32. Now let us pass, we want to pass this in our neural network, and my neural network should give me this. So but I cannot pass directly integers to my neural network. That's not how it works. I need to pass vectors. So for that, what I will do is I will introduce a new topic. So let me import torch dot nn dot functional as f. And now what I will do is, first of all, let me explain you how this actually works. So forget everything from above. So uh, f dot one hot, and if I pass a tensor, let's say 1, and I pass num classes as 27. Now what this will give me is that it will give me 27 classes, and the first index will be on. So first bit will be on. Similarly, if I pass 3, then the third index bit will be on. So 0, 1, 2, 3. So out of 27, everything will be 0. The third index will be on. So this is how it works. So here, instead of this, if I pass my x, which is my input, if I pass my input, then it should turn appropriate bits on. So first it should turn 0th bit on, then it should turn 5th bit on, 13 bit, and so on. So when I do this, I expect that in X I have 32 samples. So for each of my 32 samples, I should get 27 27 columns. So for first sample, 0th bit should be on. So this is the expected shape. So let us run this, and you can see that we have first bit on, so index 0, index 5, 5 bit on, so 0 1 2 3 4 5. You can see how it works. So let's store this in variable x and enc, which means x encoded, and let us also verify the shape. You can see 32 by 7, 32 examples, and 27 long vector. So for each input we have 27 we have basically 27 long vector representing each input, and this long 27 dimensional 27 long vector we want to pass in our neural network. Now there is an important concept in neural network which is called weights. So what you can think of weights is that when we pass, okay, let's say we pass this 0, then we want 5 as an output, right? So now 0 is going to be a long 27 vector. Then we can think of a 0 as 27 input. Now when we pass this 27 input on one neuron, then each input to that neuron will have a strength of connection, and that those are called weights. So if 27 inputs are going on one neuron, then each input will affect the activation of that neuron. And what really affects the activation is the strength of the connection between the input and that neuron. So let me explain you how it exactly works. So first I will initialize weight. So torch dot rand n. So here what I want is that I will have 27 inputs, and for now let me create one neuron. So when I do this, and when I print w, I have a long column vector. So if for my first input to one neuron, this is going to be my connection strength. The second input will have this connection strength. The third input will have one connection strength. So basically these are just one input, but one input is 27 long dimensional vector, and you can think of this as 27 inputs, and each of these have this respective connection strength to that one neuron. Now let's suppose I have 27 neurons, then I will have 27 by 27 long matrix. So I hope you understood the point. Now what we want to do is we want to we want to apply linear transformation. So similarly as y equals to mx plus b. So here what I want to do is this is called basically forward pass. So I want to multiply my input matrix multiplication with w. But before doing this, we need to check if we can do this or not. If we can we can do this matrix multiplication or not. So my x encoding will be of shape 32 by 27, and w is going to be by 27 by 27. So when we're doing matrix multiplication, the inner dimension should match. So in this case 27 27, so the inner dimension has matched, and so the output would be 32 by 27. Now what does this 32 by 27 mean? Which means that for each of my 32 inputs, I have 27 neurons giving 27 different activations for each of my 32 inputs. So for first input, first neuron, every neuron will give activations. So 27 neurons will have different activations for the first input. And this is for 32 inputs, there will have 27 27 neurons will have 27 different activations. And what does the activation depend on? It depends on weight. So neural network is all about identifying the appropriate weight so that we can influence the activation, because at the end activations will influence the loss, which we will discuss obviously, but I hope you understood this. So here we are doing matrix multiplication. Now there is an important thing called bias, which we are skipping right now. I will introduce you bias in the next video. So here, if we do this matrix multiplication, I will store this in H, or this can be called logits. So if I if I see the logits.shape, okay, so here is a problem which I expected. So this and this data type doesn't match, which you can see that this weight is float, but my X encoding is integer. So here what I want to do is I want to convert my X encoding to float as well, so that I don't get type mismatch error. And you can see the logits shape is 3227, which means for each of my input I have 27 neurons giving different activations. So these logits are basically, if you visualize logits, these are just random numbers, positive, negative numbers. So to convert this negative numbers to positive numbers, I will do exponent. So you can see I will get positive numbers, and then I will store in variable counts. Ooh, magic. So this counts is similar to this. Obviously this is not perfect, this count, because we are doing through neural network, but obviously we can improve the neural network. But initially this count represents exactly this count. Now remember, from this count we converted into probabilities. Now to convert this count to probabilities, what I will do is the similar approach. Props will be my counts divided by counts dot sum, keep dimensions as true. So I will get probability distribution. This is something that I did right here. So I have got the probabilities, and by the way, in neural network these two steps combined is called softmax. There is an efficient way of doing this, but for now I hope you understood the concept. Now let us also see what loss we are getting. So to get the loss, okay, so first of all I want you to visualize how probabilities look. So probs, this is how probability looks. So I passed the first input 0. So when I get past the first input 0, then I expect 5 as an output. So fifth index should be my output. So this is my probability. So 0, 1, 2, 3, 4, 5. So my model is this much confident that the fifth index is the right answer. And similarly, when I pass 5, 13. So if I go on 13th index right here, then 13th index in this, then that will be the how much confident my model is when I pass this 5 input. So to see all the probabilities, so what I can do is I want to index in probabilities torch dot arrange for each of my let's 32. I want so let's not hard code this. So I will do x dot shape 0, which is 32, because we should avoid hard coding. So 32, and then the actual label, which is y. So if I do this, you can see that these are all model confident, how confident my model is on right right outputs, the actual labels. Now if I log, and if I sum this and divide it by the average, which means dot mean, this will give me log likelihood. And if I do this negative, this will give me negative log likelihood, which is loss, which is something that I want to decrease. So I will paste it right here, and let us see the loss. You can see the loss is 3.71. Previously the loss was 2.45. The loss in neural network architecture is higher than what we did before, but this time we know how to decrease this loss, because the why we followed neural network architecture is because we can now decrease the loss. So we should not be worried that the loss is this. Now we can decrease this. That is the main thing. How to decrease that? Well, we can do backward pass. So what we can do is we can change the strength of connections, and then we can reduce this loss. So here I have to pass a second parameter called requires grad as true. So when we do required grads as true, so uh, every equation that we are applying here, so every mathematical calculation we are doing, it will keep track of a computation graph. And later when I do loss dot backward, it will calculate gradient. Now gradient will show me in which direction should I move, and then when I multiply that with the learning rate, that will show how much fast should I move in the. So I will exactly explain you, so I'm getting too carried away. So first of all, in after so first of all I want to do w dot grad equals to none, which I will explain this line just right after. Now what I want to do is I want to call loss dot backward. So when I do loss dot backward, what it will do is it will go back the computation graph. So basically, first of all, it will create computation graph of every mathematical multiplication division we have done. Then it will go back to the computation graph, and then it will create, yeah, it will calculate the gradient. Now gradient is the direction. Gradient is basically the slope. So now this will calculate the gradient, and then it will store the gradient in w.grad. So we don't want the w.grad to be after doing one loss backward, so we want to do none. That is why we want to clear the grad, so that is why we have done this. And now we want to update. So what we want to do is in w.data, my actual weight will be stored in w.data, and then what I want to do is I want to apply learning rate. So learning rate is 0.1, which is a hyperparameter which we can always tinker around, and then I will multiply with w.grad. So w.grad is the direction which we want to move on, and then we'll multiply with learning rate. And when we add with the previous data, which is the previous weight, we will go up up the loss in the loss curve. We will go up direction, but we don't want to go up direction because uh, we want to decrease the loss. So to go down the hill, we want to do negative. So in this way we will go down the loss curve. So this is how neural network works. So print loss dot item. When I do loss dot item, now okay, so let me run this. When I run this, okay, I'm getting an error. So the error is does not have required grad fn. So I think I need to run, I didn't run this cell. And when I run this cell, you can see that I've got the loss 3.69. Now this is the initial loss. I can decrease this. When I run this cell again, 3.68, 3.67, 3.74, 3.66, we're going down. You can see this is the magic of neural network. Every time, initially we start with some loss because initially the weights are random, and so initially we expect the loss to be quite high. So initially we expect that we are on quite high altitude on the loss curve, but each time we want to change the weight, we are changing the weight, and each time we're optimizing the weight, and each time we're going downhill the loss curve. So that is why we're seeing that the loss is decreasing. So every time I run this, I'm getting a low loss. So you can see this, we're getting a low loss. So let me do one thing. Let me run this in a loop. So for I in range, let us run this 10 times. Loop, and if I run this, you can see 3.59. So looks like you can see there is no much decrease in the loss. That is because we can always change this learning rate. So let me change to 10. So if I do this, you can see that loss is going down, and loss is going very low. I don't expect loss to go this low. And reason why loss is going this low is because we just have 32 examples to work on right now, because we're just using 5 word. So now let us use all the words. Let us run this cell. Now I don't want to run this to cell, but if I run this shape, we can see that I have this many examples of bigrams, and we have labels. Let's convert that into 27 long dimensional vector. Let us initialize weights, and then let's run this. So you can see the loss started quite high, but each time we're going downhill, loss is coming down. So in this way, loss is coming down. We had the loss of 2.45. So let's aim to come to that point. 2.67, 63, 61. Okay, so let's run 20 times. Okay, 2.55, 2.53. So now let's lower the loss, because when we are about to come to the local minima, we don't want to come we don't want to uh, we don't want to have a higher learning rate. So 2.52. So looks like we're not decreasing from this point, but obviously our neural network is learning. So now let us sample. So previously when we sampled, we could see that the name were not name like. So now let's sample. So I want index to be 0, and let's initialize out while loop. So first of all, I want to pass dot as an input, right? So 0 as an input. So let's copy this. This is going to be exactly the same. Copy this. So first we okay, so 0. So first of all, we will f dot one hot encode this index, and number classes should be 27. When we one hot encode this, so this we should get x encoding. So the same that we did right here, but we need to convert this into float, and then we multiply this here. So basically this will be of shape 127, and when you multiply with the weight, the shape would be x encoding would be 127, and then when you multiply with weight, so each of our 27 neuron should give 27 activations for this one. So literally my x encoding is 127, and then my weight is 27. So my output should be, for my one example, 27 activations from 27 uh, neurons, and the count should be 127. The probability distribution would be 127. So we've arrived at the same point. Before, the probability distribution was we found from the P2 dimensional array. Now we get the probability distribution from the neural network. Now we'll do the same thing. Torch dot multinomial will pass this probability distribution, and num samples would, we want 1, and item because we want the number of the tensor. This will be my new index, and let's append this index to out, and if index is 0, then we want to break, and at the end let's print. So let's zoin for each index in out, and integer to string mapping index. So when I do this, okay, I get an error. So input must be a tensor. So okay, this must be a tensor. So torch dot tensor index. So when I run this, I get an error again, dimension out of range. So dimension out of range. Okay, so this should be 0, not 1, because this time we're getting just one row. So it should be 0. So when I do this, you can see I get a name ZA. So let's, for in range, let's print out 10 names. So you can see I'm getting little good name than before. Bi base, kin, katin, enanti, aquarium. So even if the loss is not less than before, my neural network is able to produce a little bit better name than before. Agree? That is because now my neural network can understand the context between each characters little bit. This is not a perfect neural network, but little bit it can understand the context between each characters. So it can understand the association between T and A. That is why it is coming up with this name. So that is the essence of neural network. It's just not predicting the next token, it is actually understanding the context. But this time the context is one, because we're predicting from looking at the previous character, we're predicting the next character. But once we uh, complexify this, uh, like if we look at three characters and then predict the fourth one, then maybe the name would be better, and it would which means that it can understand three character context. So in that case, even if the loss would not go down, it could really understand the meaning between those three characters. So that is how neural network actually is beneficial than this raw raw scratch count probability prediction. So that was all for this video. Now in further videos we will look at this is a bigram. So based on previous character we're predicting the next character. But in upcoming videos we will look at previous three characters, predict the fourth one, and then after that we'll go on transformer, recurrent neural network. So we will complexify, we will learn everything piece by piece. So I hope you understood about this video, everything I discussed on this video. uh, i i I intended to keep very simple. This is exactly like Andrej Karpathy video, but this time we're doing it our own way. This is kind of summary, more handwriting code. So I hope you understood this. So I'll see you in the next one. Thank